Good morning. Welcome at the second session. Thank you for joining me. I see you using the chat box. Thank you. Thank you. And yeah, I see the message about updating the photo. That's good. Good. Thank you. I saw a couple of students updated photo, a couple of students put the discussion post, a couple of students introduced themselves. Okay, that's when I see the improvement. That's important, yes? Always a little bit, consistency. That's probably the word of the week. Okay, that's what we will do. We will keep working on this presentation, and we remember from yesterday, this is just a review, like a broad review, quick review of chapter 1 of algebra. And next week, we will start calculus. An honor log. Okay, Margot, thank you. And the honor log. I didn't check the honor log, but I'm assuming we have more students. Okay, that means if you really would like to practice, I will definitely make sure that you can solve independently, like just on your own, all of the questions from this presentation. Yeah, it is called Week 1 and it's posted on Canvas. That's important. Additional slides that I have, additional notes for each section from chapter 1 it's like more details, more questions, but definitely this type of question. And we will go really quick and we will solve one per topic, okay? Because I have a couple of questions per topic, but we will try to just touch the concept. Okay, let's start. Any question, you can use the chat box. And if I will ask the question, you can also try to answer using the chat box. Okay, let's see. Domain, we did start with this rational inequality. And we did have a little bit of, not problems, but yeah, we did, finally we did solve it. That means, please remember one more time, when you have inequality and it's different than linear inequality, we always have to keep 0 on the right-hand side. Yeah, that's the easiest way. Then we're trying to create a quotient or product. If it's polynomial, we will factor out, we will get the factored form, product form. When it's quotient, when it's ratio, we will have a ratio, we will have a quotient, and we always need zeros. Yes, we need the zeros. That means that the roots, that means 2 and 0. Placing on the number line and testing each interval, because these zeros are really important on the number line. They actually change the sign, and we want this ratio to be positive. Yeah, that's when we can see, we can test it. Let's maybe before we do, let's come back here. And for instance, yeah, let's do both maybe. Let's do both. Maybe B is easier. Okay, what about this domain? Yeah, just checking, just the warm-up for today. We know that the quantity under the square root, which is called radicand, must be positive. That's when we do have 2 of them. 7 minus x must be greater than or equal to 0. And at the same time, that means both of them, they have to be correct, have to be true. Quantity x squared minus 16 has to be greater than 0, and I cannot accept 0 because it's in the denominator. Okay, that means we theoretically have 2 inequalities, but we have to combine them as a final result. Okay, the first one is this a linear inequality? Is this linear inequality? Yes, yeah, we can solve it like a linear inequality. We can just subtract 7 from both sides, and now we will multiply by negative number. What is happening when we multiply inequality by a negative number? We will change, yes, we will flip the sign. That means from this, we can accept all of the x's less than 7. This is 7. We may accept this and less than 7 is here. But we still have to, I can write, it's okay, I can skip the interval notation. Yes, we will change the sign, definitely, but we will also change the direction of inequality. Okay, from negative infinity to 7, including 7. But that's not everything, because we also have to respect this statement. And now, how we can solve this inequality? X squared minus 16 is greater than 0. Yeah, it's not a linear inequality. Yeah, that's we would like to get a product. We would like to get the zeros. Let's factor out x minus 4 and x plus 4. Yes. Yes, that's definitely Math 22, Margot. Yes. Yeah, which is extremely helpful in our calculus class. Okay, and we remember we see 2 zeros, we see 2 roots. Yes. I mean, I can just write them. They are not the solution, because the solution for the inequality is an interval. But we see negative 4 and 4, which we will place on the number line, negative 4 and 4. We will not accept them because we cannot have 0, just greater than 0. But these are the numbers, they are dividers on the number line. Let's test each interval, because we need positive quantity. Okay, when I substitute 5 minus 4, 5 plus 4. It's positive? I think it is positive number. When we substitute a number between negative 4 and 4, for instance 0, 0 minus 4, 0 plus 4, and multiplying, I think it's negative. And then when we substitute, for instance, negative 5 minus 4, and negative 5 plus 4, negative number, negative times negative is positive, okay? And we're looking for the positive. Greater than 0 is positive quantity. Okay, that means we will have from negative infinity to negative 4, and from 4 to positive infinity. But let's just put this together. Okay, we have negative 4, 4, and 7. We can accept all of those numbers, because that's the first one, and we can accept not including 4, negative 4 and 4. That means that wherever we overlapped, that's the combined solution. That's we can accept all of the numbers from negative infinity to negative 4, not including parentheses, union. And from 4, we can see up to 7, including 7. This is the domain. Yeah, such a simple question, but the solution is, yeah. But we always need the product form, factored form. We need this, and then we have to look at the zeros. If we have to solve inequality different than linear. Where did the negative 7 come from? Oh, negative 7? Where is negative 7? Oh, the first step. I did subtract from both sides of the inequality. Okay, okay. I thought that I put negative 7. No, it's, yeah. Yes. Okay, yes, good question, good question. Okay, and then let's quickly do, now we know what to do. Quantity, which is the radicand, x cubed minus 16x must be greater than or equal to 0. That's the concept. Now that's the art. Now it's the work. Yeah, mathematics is always, that's the reason that is so like, I don't know, it's considered like maybe difficult, because we always have to set up things. Yeah, we have to be, and then we can solve it. Okay, what we will do for this one? Yeah, it's the third degree polynomial, definitely not the linear. Let's factor out. Let's find all of the x's that makes this quantity 0. Yeah, because 0, on the right, on the left-hand side of that zeros, of that roots, the quantity will change the sign, but we need only positive. Okay, we can factor out x. And we still have quadratic, which the way that we can factor out looks like this. X times x minus 4 times x plus 4. How many zeros we have? How many roots of this equation? I can place them on the number line. We have -4, 0, and 4. And we may include, we can see all of them. The endpoints will be included. Then we can use the bracket. We never bracket, we never close the infinity or negative infinity. Okay, and let's test. Let's test. When we substitute 5, yeah, I'm substituting instead of the variable x. That's when I substitute the test value 5, positive. When I substitute the test value 3, negative. When I substitute the test value may be -1, positive. And when I substitute -5 is negative. That's my calculation, really quick. Okay, you can check, but you probably, yeah, you can check, and I believe it is true. Okay, and we're only looking again for the positive. That means positive is between -4 and 0, and from 4 to infinity. From -4 and 0, or actually including, yes, including brackets, union, 4, and not, yeah, infinity we will not close. X belongs to a little bit of set notation. Beautiful. And not just greater than 0. Because we may, greater than 0 means that I can accept 0. Square root of 0 is 0. Yeah? Makes sense? And square root of 0, I can have 7, for instance, because 7 minus 7 is 0. Square root of 0 is 0. But for this one, 4 and -4, I cannot accept them. 4 squared minus 16, it is 0. And square root of 0 is 0. 0 in the denominator, we're not allowed to have 0. Okay, makes sense? Yes, okay. The line under the inequality means equals to, yes. Okay, yes, yeah, you answering. Yeah, that's equal. But the question was why here? Yeah. Union is like addition, this and this. Oh, actually, I have to be more logic matter. It's or. Yeah, I mean, means that union means that we accepting this interval or this interval. We accepting both of them. Of course, I cannot say and, because we cannot have numbers between -4 and 0 and at the same time greater than 4. That's not possible. But we may accept these numbers, or that's union, or we may accept this. Union means basically or. Yeah.
So we have just to clarify, so we have the the negative on the left, or which is union, and then we say the positive integers.
Yeah, we may have these numbers, or we may have these numbers.
Okay.
The numbers from that interval or from this interval will satisfy this inequality, meaning that this quantity will be always positive because we set up this inequality. Okay? I hope. Okay. Yeah, it's just, yeah. Okay, that's the way to solve the inequalities. Yeah, we will have them, as I said, later for some derivatives, integrals, some applications. That we have to be good with this. Okay, and then you can practice. I skip this one. I skip some of those. You can practice, you can check my writing, my solution on Canvas, okay? You can do this one, that's beautiful. You can do this one, okay? Oh, this one is nice. This one is similar that we did yesterday, okay? Try, please try, and then check against the solution. Even more. As soon as we see product quotient, just pick up the zeros. Yeah, that means please do not be afraid. Oh, wow, it's too complicated. We can see, yes, we can see right away the numbers that we can place on the number line. Actually, what numbers you will place on the number line? Please tell me. -5, correct. -5, 6, correct. And one more. -3/2. Which one we may accept them? Because these numbers are the zeros. That means when I substitute, I'm getting 0. Which numbers we can accept, which one we cannot accept? I know the radical expression is, it's fun. Let's say this way. Okay, which one we will accept? Which one we will put the bracket? Accept, yes, we can accept. We don't have, the 0, that means we cannot accept 6 because 6 will give us 0 in the denominator. But we may accept -5 and we may accept -3/2. And now you have 1, 2, 3, 4. You have 4 intervals, you taking a test value, any number from that interval, substituting and checking if the quantity is positive or negative. For instance, this one will be positive. Okay, and so on, because we want this expression to be greater than or equal to 0. And then you can, that means definitely, I don't know the rest of them, you can try, but union from 6 to infinity. But you have to test the other one, wherever is positive. Because when we substitute big number greater than 6, each factor will be positive, we will have, yes, positive. And we can accept. Okay, you can check. Okay, you can check this. Okay, let's keep moving because I have lots of things to do. Okay, now let's look at this one. Yes, because we're talking about some inequalities, linear inequalities, non-linear inequalities, but in general, linear function. We have to be confident. That means we know it's just the line, correct? What is the equation of the line? Can somebody tell me? What's the equation of the line? And general, I mean, we have a couple of forms, but yes, the most general is mx plus b. Beautiful. What is m? M is the slope. M represents the slope. Changes in y over changes in x. Changes in, like when we have the same the same difference between the inputs, the x values, and the slope supposed to change, the y values supposed to also have a constant change. Not the same as x, but constant change. And b is the y-intercept. The value for the function as x is 0. Okay, that means looking at the values from the table, do you think we see the line? Or not really? It's not enough points, right? Because if we will plot them, we can try to draw the line, but that's not really the way. Let's look at the values. First of all, let's look at the x's. 0, 1, 2, 3. Yeah, they change by 1. That's good. That means I can actually say this is 1. Okay, they changes by 1. What about y values? Is the difference, the change the same? 27, 25, 23, 21. Yes, they changing by 2, but positive 2 or negative 2? Yes, we can see we have to just subtract 2. When we jump 1 unit along the x-axis, 2 units down. 1 unit, 2 units down. That means this is -2. Yes, it's definitely, I think I type it, yes. Values of x and y in the table could come from linear function if difference in y values are constant for the equal differences in x. Yes? Okay, and we may get the equation. It will be -2x. Do we see the y-intercept? I think from that data we see right away. What is the value of y if x is 0? Yes, thank you. Okay, that's we good with this. Yes, but the slope is important because we will grab that concept next week. Okay, what about B? 15, 20, 25, 30. That's, let's maybe this was A. Let's do B. I see that changes in x's are by 5. What about changes in y? Do we have the same? The slope for the first one is -2 because we have 1 change in x, -2, 2 units down. 1, 2 units down. Okay, but this one, we can see this one is changing by 10, +10, +10. Yes. Okay, that means slope. It will be changes in y over changes in x. For the part B, the slope is 2. Okay, right? That's definitely it's the line 2x plus b. But who can tell me what is b? Yes, we're not guessing. This was easy. I mean, this was obvious because the value for 0. For part B, we don't have value of y for the x equals to 0. I think it is 32. Yes, it is 32. How we can get the value? We have points that we can just use. For instance, we can use the first one. When x is 15 and y, corresponding y is 62, we can put 62. I can just use this equation. 2 times 15x plus b. And you can solve for b. It will be 32. Yes, I'm just 15 and 62. Y is 62. X is 15. Okay, and the equation, final equation is 2x plus 32. Beautiful. Okay, and what about C? 1, 2, 3, 4, x's. Yes, they have the same difference. But what about y's? 5, 10 plus 5. From 10 to 18 plus 8. From 18 to 28 plus, it is increasing, but it's not a constant. Yes, it's not a constant rate. Okay, that we don't know, we will just, yes, this one, yes, yes. C is not linear expression. Okay, we good with this? Let's keep moving. Yes, let's maybe do one application. Okay, because I have a couple of them, but you will do the next one. Okay, that's what we have. In 2015, the population of a particular city was 2 million people. Between 2015 and 2020, the population was increasing at the rate of 200,000 people per year. Constant, yes, we can see constant increase. That's the message for us that, I mean, we may figure out what model, linear or not linear. Okay, find a function p of t, the population in millions of people of the city y, y years between 2015 2020. Oh wow, we have function that fast. I think it's correct, but let's see. This is definitely the key, part of the sentence, the key sentence that is telling us that the model is linear. That's we will say MT plus B. Okay, T is the variable time. And it will tell, that's actually, that sentence is telling us the slope. Okay, that's what's the change? The slope is changes, or maybe I can say changes in the population over the time. Okay, yes, that means this one will be 200,000 people per 1 year. Perfect. And we can say because it's in everything has to be in millions. That's when we move millions has 6 zeros, 0.2. That means 0.2 million. That's what we can say M is. Okay, that's when we do have 0.2 T, and the beginning of the data is 2015, correct? And what was the initial population in 2015? That's I can just say 2, because B is 2 millions, but we will say 2 million. Okay, that's we do have a function. That's it. That's what we need to do. Find the population, yes, between 2015 or 2020, but we don't have to do anything with 2020. Between the years, this is just telling us the time, yes, frame. 2015 is 0, and if we have to do something with 2020, what will be the T value? Can you tell me? Can you help me? We don't have to do anything. They don't ask me. It will correspond to 5. Thank you. This is 0. This is 5. Really good. Yeah, that's we're not using 2020. We will use 5. Yeah? If we have to do some computation exactly at 2020. Okay, yeah, that we can see. This, the boxed part of this text is just telling us that is linear expression, linear model. Okay? Model means just equation, expression. And that's, please do not be like afraid. Sometimes students are afraid of the word model. Okay, let's keep working. Okay? You can do this one. The same thing. You can maybe do this one if we would, because it's relatively easy. Okay, you can try. I know that you can do it. You can solve this one. You can complete the square. Okay, because we still have exponential function to see a little bit, and we still have trigonometric. That's when I just want to have time for this. Okay, exponential function. Yes, we know how exponential function looks like, I hope. I have some formulas. I can even, it's okay, we can do here. That means this is the exponential model. In general, I can say y equals to b a to the power of t. Actually, because it's always time, always application, let's say x. Okay, that means if x is placed in the exponent, that's the exponential model. That's the easiest way. If x is 0, and like the initial value, if x is 0, what is a to the power of 0? Assuming that a is not 0, because that's different. Yes, it is 1. That means 1, then the initial value, if x is 0, is always that quantity. We can even see p sub 0, yes, the initial quantity. Because when we substitute 0, we're just getting p sub 0, or the, in general, b, quantity b. Sometimes you can even exchange this, a and b, depends of the, whatever you set up, the labels, the equation, then you can carry on with this notation. Oh yes, biology definitely use the exponential, because we will see later, and maybe also in calculus too, we have lots, like in nature, lots of things behaves exponentially. It's fast. I mean, we do have some limitation, but yes, nature, science, biology, the growing of population is, okay, but now let's look at the details. That means this is the exponential function. One thing is important, the base is never 0, and it's also never 1, okay? That base, this is just like a given based definition on the exponential function, because if a will be 1 to the power of any number is always 1, then we will have just a constant function. Yes, and we actually need that exponential growth, never 0 and never 1. And actually a is always positive. That's another definition. Never, yes, of course. That means a is always positive. Okay, positive. This is again just the definition. That base is never negative, because what's happened, x could be any number. If we have application, the variable x is actually t, is time, then we applying only positive numbers. But in general, let me actually maybe draw, let's say just 2 to the x. We remember this. That means it's function like this. 2 to the power of 0 is 1. Okay, like if 2 to the power of 1 is 2, 2 to the power of 2, oh, it's supposed to grow. We can see how fast it's growing. What is 2 to the power of 3? Can somebody help me? It is 8, yes? We can see how fast. 2 to the power of 4, oh, it's supposed to be higher. 16, yes? That we can see, we're just going like 1 unit jump along the x-axis, and how fast is like changing the height, our model. 2, 4, 8, 16, 32. Yeah? Okay, but what I was going to say, let's just, yes, always positive and never 1. That's what we're supposed to. And x could be any number. The domain for the exponential function, general exponential function, is all of the numbers, because we remember we just did the domain for the algebraic function, for the linear, nonlinear, but for the exponential, yeah, we have to just know. And since x could be any number, we don't want the base to be negative. Yeah, because then we will create really chaotic situation. Because if x is, for instance, 1/2, let's say we have function 4, yes? If we will have -4, yeah, that doesn't exist, that number, because 1/2 is the even root, square root of 4 to square root of -4. We're not using any complex numbers. Yeah, no. That means that's the reason that the base must be positive. Okay, just the review. Let's do some application. Okay, that means this is the general function. And if that base is greater than 1, yes, if it's greater than 1, we always have this growth, just what I draw, 2 to the x, for instance. Yes, we always have that growth. If the base of that exponential function is less than 1, but still positive, we can see still positive, but less than 1. For instance, 1/2. to the power of x. Then we have decreasing, then we have decay. Still 1, but the model looks like this. That means it's the growth if the base is greater than 1, or it's the decay if the base is less than 1. It's also the population, growing population. Okay, also what we will do for some application, that base can be defined as a 1 plus the rate or 1 minus the rate. If the rate is like, if it's increasing, yes, the rate will be, of course, a positive number, and it's exponential growth, the same like this. When the rate is like, when we decreasing, then it will be negative. We will subtract. Then this number will be less than 1. It will be exponential decay. Yeah? And it's, again, it's really, really powerful function. Yes, really powerful, powerful function. And I can show you one thing. Do I have this? Yes, I have it. Oh, okay, I can show you just for the fun. Again, just to motivate the consistency, the continuous, like, let's look at this one. Yeah, you probably heard about the 1% rule. Yeah, that's in when we starting, let's say we're starting with like 1, whatever we have, knowledge or weight or some, we would like to have some progress, and we're starting with like 1. And if you improve, yes, if you will put the effort only 1% per day. Yes, I hope it's, I always love this. Only 1% per day for the entire year. Look, this is like 1.01 to the power of 365 number of days. Look at this number. You can even check on the calculator. 1.01 to the power of 365 is 37.78, or like 38. Yes, and it's just 1%. For instance, when you exercise, when you do, I don't know, when you can maybe do 5 push-ups. Yes, then try to do, maybe push-ups is not, yeah, because 1% is not, yeah, but then try to do 6 in a week, or like when you do maybe squats, yeah, you can do 10, you can do like 11. Yes, like next day, or anything, of course, with the mat. Yeah, you can spend a little bit of time and a little bit more. Then the improvement is huge if we stay consistent. Yes, if we have this continuous like improvement. Okay, that means please be consistent. Now, the bad thing is, I mean, the worst part is when we avoiding, when we not doing things, and even if we not doing a little bit what we supposed to do, yeah, like only 1% less effort. It's easy to do 1% less effort. Yes, every day. Then look at this after 1 year. Yeah, this will be that. You will, from 1, whatever 1 means the whole, like something. You will even like, yes, downgrade like all your skills. Yeah, all this one is 37.78. 5%. Yes, you can add 5%. Definitely the large goals are, yes, not good. Because when we think, okay, I will not do today, I will not work tomorrow, I will not work day after, and then I will work like weekly or bi-weekly. No, because the large goals, we can end up with burnouts, frustration, and of course, yeah, it's a good recipe for failure. For failing. That's in, please, yeah, tiny step. I know that it's difficult. I really know that it's difficult, because the small steps, like sticking with these small steps, fundamentals, they are not noticeable. We will not get headlights for this. Yes, but when we are consistent, when we get back and when we look back, even after 1 semester, like almost 6 months, almost like half of the year, it will be a big improvement. Yeah, we can see this, yeah, this one or this one. Yeah, like kind of like half of the year. Okay, that means please be consistent. That's the message of this week. We will have message for every week. Okay, but 1% rule. And this is amazing. Yes, that math. Okay, let's do it at least one question. What we doing? Okay, let's see. Okay, then I have a couple of formulas. You can check them because I don't have to really explain. It's everything. That's the same thing. Oh no, actually, one more formula. If the change, yes, it's not like by day or by week, by 6 months, by 1 year. If the change is like continuous change, that's especially like in the nature. If the population is growing, yeah, like that's let's say the bacteria is growing, it will not grow for 5 minutes a day, or it will grow continuously. That's when we have continuous change, continuous growth or decay, we will use the natural exponential function. Okay? That means it's the same thing. It's the population, initial population, and this will be E. E will be involved. E to the power of K or 8, and then time. Yeah. Yes, this is, but we don't have to really like go really deep. I just want you to know that we have these formulas. Yes, E to the power, and actually we can, usually I will write E to the power of RT. R means the rate. I think our textbook was using K, but K is the rate. Yes, it's basically the continuous rate, continuous growth or decay rate. Yeah, we will see. That's it's similar, but instead of just the base, like 1 plus the rate, 1 minus the rate, we will have E to the power of R. And we have nice connection, but yeah, we will not. You probably has this at Math 22 or any pre-calculus class. Okay, that's the continue. Oh yes, we have RT. Okay. And yeah, let's try to look at this one. Because now what is important? We have to figure out, looking at the data in the table, we have 4 functions, f of x, g of x, h of x, k of x. Which one is the exponential? Okay, which one is the exponential? That's when we're just looking at the exponential. And exponential function change by like percent. Yes, the percent change is the same. Yes, we have the common ratio. Okay, that's what about the first one? What do we think? X's are not, we don't have to focus because they are good. They're changing by 1. That's the Y values. 1, 4, 9, 16, 25, 36. What do you think? What formula you will give me? Do we have this common ratio? I think it's just the square. It's 1 squared, 2 squared. Yes, that means this one is not. This one is just the power function. Yeah? X must be in the exponent. Okay, the percentage rate, the percentage change is the same. Okay, 2, 4, 8, 16, 32, 60. Power function means that power is like polynomials. X squared, x cubed, x to the power of 2, 3, 4, 5 positive integers. That's the power function. F of x, x to the power of n. That's power function. And n it's the natural number, counting numbers, 1, 2, 3, 4, 5. That's the definition of the power function, like polynomials. Yes, at the addition or subtraction of the power function. Okay, 2, 4, 8. What you can see, what I mean by common ratio, when you take, for instance, 4 divide by 2, 8 divide by 4, 16 divide by 8, 32 divide by 16. Do we have the same number? Or in order to, from 2 to get 4, what we will do? In order from 4 to get 8, what we will do? Double. Double means multiply by 2. That means this one is just 2 to the x. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, times 2, times 2, times 2. This is exponential. Yeah, because when we take 8 over 4, when I take 16 over 8, 32, it's like a geometric progression over 16. It's called, yes, this will be that base. Yeah, it is 2. What about if 62, it falls outside the rule? Oh, no, typo. 64, oh, no, it is a typo. Good eyes. Oh, I didn't even, because it has to be, oh no, it has to be exponential. Oh, wow, I didn't even see this because I really wanted to see 6. No, it's 64. Thank you, Reese. It's supposed to be 64. Okay, what about the next one? No. You all, yes, good students, and no, we cannot think this way. I'm not gonna even repeat this. Okay, what about h of x? Yes, that's the correct definition. If x is in the exponent, it's exponential function. If x is in the base, it's the power function. Okay, yes, this one is again power function because we just taking cube of the numbers. And what about the k of x? K of x is yeah, a little bit, but we can see when we divide 12 divided by 6, 24 divided by 12, 48 divided by 24. Yes, we still have, that means k of x, but let me put this, b a to the power of x, because for this one, the quantity b was 1. This one we have to be careful 2, because we know that is 2 to the power of x, because that's how we getting the rate. We just dividing 2 to the power of x. But when x, let's see, when x is 1, the value is 6. When x is 1, that means b, 2 to the power of 1, the value is 6. Yes, I just apply. That's what will be the b quantity, the initial value. Yeah, we're not starting from 1. We probably have to adjust. That means it's not just 2 to the x. Yes, thank you. b is 3. That means the final answer for this one is 3 times 2 to the x. Just initial value is different. Good, G. But how did you guys figure out the others, I think? No, we just have to kind of like look for the pattern. Yeah. Look for the pattern, and yes, exactly, just finding the pattern. Yeah, kind of like IQ test. Okay, but what we're looking for this common ratio. We're looking for this exponential model. That means this one, when we divide them, yeah, it's the same. I mean, we always have to divide one number, one output behind by the output in front. That means 12 divided by 6, 24 divided by 12, and so on. 96 divided by 48. And this will give us the base of the exponential. And then we have to figure out the initial value. Okay. Oh, that we can, I was planning to do, That's what we can do. This one you can try. Okay, I was planning to do this question. We can do this question. That's what we can do. We can finish with this question. And what I didn't actually, I was planning to do the trigonometric functions also. But if you don't mind, we can meet tomorrow at 8, okay? Or I can just put the video together to review the trigonometrics. But I will be doing tomorrow at 8 a.m. Okay, because we remember we can have additional session if you have any classes or if you have some other things you don't have to attend, you can watch the video later. Okay, but I will be doing just the trigonometric functions review tomorrow at 8. Okay, that's me. Let's just finish with the exponential. Let's finish with this question. Yes, you don't have to because it's maybe too much. Yeah, but just because we had nice conversation. Okay, that's in tomorrow at 8. You can check the video later. It will be placed in media gallery or maybe on my YouTube list. You saw the list. Okay, let's solve this one. That's what we have. You are testing a new antibiotics. And in the particular experiment, it is able to kill 50% of a bacteria population every hour. Okay, every hour. Assuming that at the start of your experiment, there is 100 million bacteria, find function B of t, giving the bacteria population in millions as a function of time in hours from the start of your experiment. My reading. Okay, that's we have to find a function. And we can definitely see the percentage change. It will be, we have the function really fast. I think because killing means killing, that's not nice word. But killing the bacteria, this is good. Destroying the bacteria 50% an hour, it's increasing the number of bacteria or decreasing the number of bacteria? Okay, that's it's decreasing. That's we can say that rate is negative 1/2. 50%, half. Yeah, that's we do have a rate. And we can say initial population 1 plus the rate to the power of time. Yes, we remember this. Okay, what is the initial population? Do we know the initial population? It starts, 100 millions. That we can just put 100 because everything is in millions. And then I can put 1 minus 1/2. Okay, that means yes, somebody gave us the answer and it's the correct answer. Okay, 100 1/2 to the power of t. Did somebody give us? Yes, Lara gave us. Good. That's the model. As soon as we have model, we can do everything. Okay. But we can see, maybe I can write it down. Let's say b, a to the power of t. But a is 1 plus the rate. This is the function. And rate was negative. That means it is decreasing, it is decay. Okay, how many bacteria are there 4 hours after the start of the experiment? What we have to do for part B? Just substitute 4. Can somebody maybe use the calculator? Or maybe we don't have to use the calculator. Let's see, 1/2 to the power of 4. 2 to the power of 4. 16. 100 divided by 16. 50 divided by 8. 25 divided by 4. 12.5 divided by 2. Am I right? I'm just dividing by 2. No calculators. And then 6.25 million. Nice calculation. Good, okay. As you can see, no calculator, 1/2 was a nice number. 1/2 is a nice number, okay? And then part C, when there are 20 million bacteria, that's we have to know how like many hours we have to wait. The bacteria has to be 20. Equation 100, 1/2 to the power of t equals to 20. That's the exponential equation. Let's see if we can solve it. 1/2 to the power of t equals to 1/5, because I did divide by 100. And then we have to take the natural log. Yes. Do I have room? I don't have a room. Let me write here. When we will take the natural log of both sides, let's see what's happened. We will have natural log of 1/2 to the power of t, natural log of 1/5. And that exponent can travel in front. T, natural log of 1/2, natural log of 1/5. And we can just divide natural log of 1/5 divide by natural log of 1/2. For this one, if this will be the exam type question, this is fine answer. This is good. You can just leave it like this. But since it's the in-class exercise or could be the homework exercise, you can use the calculator just to check the numbers. But again, on the test, this will be good answer. But we don't know, yes, we don't know. Let's actually see. I think if you use the calculator, you're supposed to get 2.5, 2.32, 2.5 hours. Okay, Reese is asking this. Always the class presentation is the good the good source of exercise. That's when I will definitely start with this. Achieve, you still have to do your homework assignment on the Achieve. That's mean do this one. And if you still think you need more, you can like keep working on the Achieve exercise, like additional exercise. Yes, looking at the textbook but these problems that I always have during the live sessions, the lecture notes problems and plus the Achieve, that's the good source of problems to practice. Okay. That means let's finish the session. And as I said, you don't have to, but if you wish, like as occasionally we will have this additional session. Tomorrow at 8 a.m. I will cover just maybe half an hour trigonometric function, because we have nice sine and cosine model, and I would like to solve. Actually, the question is placed in this presentation. Okay, that's me. Thank you very much. Please don't be like, I don't know, afraid or scared. This is just the review, just the really quick review. Okay, thank you, and check this presentation. Next week, we will start calculus. Thank you, and see you tomorrow or see you next week. Thank you.